So welcome back. Let's go ahead and take a look at Chapter 2, Interatomic Bonding. The kinds of questions that we like to ask today is as we bring two atoms or ions together, as they approach each other and form a bond, we'd like to quantify the amount of energy that holds the atoms together. That's the bond energy. We like to quantify the equilibrium distance between the atoms. How close will they sit next to one another? If they get too close, they're going to repel as they overlap. So there's some equilibrium distance that we want to talk about. This will be obviously related to the radius of the atoms. And we like to talk about what kind of properties, even at this level of bonding, are affected. All right, so let's go ahead and look at the energy between two ions that are first very far apart. Okay. These will have some attractive energy. This is a fairly long-range force. And so we may have some attractive energy here between the particles. And as they start to approach each other, this attractive energy will continue to become more and more negative. It's a larger and larger attractive energy. Okay, so when you think about the strength of the attraction, it's the absolute value that you're thinking of. But in terms of energy, the energy is going down. Negative are favorable energies. If these particles get very close, and I should say that this separation here between the particles is R. That's what we've got plotted here on our X part of the axis. As they get very close, that attractive energy starts to become very negative. But if they get too close, then they start overlapping and we get a repulsive energy. And so there really are two terms here, an attractive energy, that's this one, and a repulsive energy, which is a short-range force, but it increases very fast with this power n, and n might be, for example, 9 in your homework problem. And what we can do is we can add these two terms. And when we add these two terms, we get the red curve that's here. This is our net energy. Net energy. All right. And so at some point, when the repulsive energy starts to kick in strongly, it will dominate at short distances. That's why this starts to go back up, become positive. Our attractive is still becoming negative, but the repulsive wins. And so the equilibrium distance is this minimum in the net energy curve. Okay, so this distance out to the minimum is R0. That's the equilibrium separation. And the value here of this well, how deep it is the bond energy, E0. And so that's where we would get the equilibrium spacing and the bond energy. Now the bond energy in your text, they will use joules and also EVs. And so I think the problems that I've given you are working in EVs. And so a typical bond energy, say, might be 3 or 4 or 5 electron volts, okay, depending on the material. All right, so that is our energy curve. Now, if we wanted to come up with, say, an equation for the equilibrium spacing or the bond energy, all we have to notice here is that at our minimum, we've got a slope down here of 0. So if we take the derivative of the net energy curve with respect to the radius, and we evaluate that at R0, this derivative will be equal to 0. Okay, so I take the derivative, I set it equal to 0, and then I solve for R. That R that I'm solving for is R0, the equilibrium spacing. Once I have R0, then I just take that and put that into the net energy equation, and that'll then give me the bond energy, E0. So we can do that mathematically. All right, for homework, you will be looking at the attractive and repulsive energies between two ions. This example, we have potassium and chloride. I don't remember off the top of my head what your homework was, but they will give you the attractive equation, the repulsive equation. And remember, again, what we need is just the net. So we're just simply going to plot. We're simply going to add these two. We're going to do this in a plot. So I'll show you what it looks like in Excel. And then I'll post maybe a video helping you actually work through Excel if you're having trouble. But in Excel, we can go ahead and make a column for the attractive, for the repulsive, and then add the two. And then plot all of those versus the radius r. And we'll generate this curve that we just saw, and then from there we can read off the bond energy and the equilibrium atom spacing. Okay, so again, this is going to remind you of the equation. This is the data that was given, and I have all of that written over here for my constants. In this case, I actually went through and did the derivative of the equation and found the equations for E0 and R0, so that's what these were for. You don't have to do that. These are calculated. And so what I need to do is just simply plot this equation. So what I'm going to do is make a column of R values, and the units are in nanometers. So I'll go ahead and do that. And then I'll make a column for the attractive energy piece and a column for the repulsive energy piece. And then I'll go ahead and add those two for the net energy. And then all I need to do is select these columns and tell Excel to go ahead and scatter plot it. And I'll get something like this here on the right. All right, now when you first go ahead and do this in Excel, what you'll probably find is that you don't see actually anything except for maybe a flat line, and then it looks like your curve kind of does that. So if you double check on the limits of the axes here, you'll probably find that they're very, very high, so that you can't see this well, which is only on the order of, in this case, say almost 0.5, I mean, almost -5 EVs. And that's because at very close spacings, the repulsive part is very, very large. So you notice the size of these numbers. So what you can do is either skip some of those when you go ahead and do your plotting, or easier is just go ahead and double click on your y-axis and change the scale to something much more reasonable, and you'll get your curve. Okay. Now, one of the reasons why we're interested in this bond energy is that it's related to some properties of a material, and we will talk about some of those as we go on. Right now, I just want to give you one example, which is the melting point. So the bond energy is the energy at which the atoms are held in position, if you like, when we're a solid. And then when we become a liquid, we have to have enough energy to overcome that bond energy, turn it into a liquid. That's the melting point. And so we get this energy by adding heat or temperature to our sample. And so once the thermal energy, right, gets added into the sample and starts to become a significant fraction of this bond energy, then those bonds can be broken, and you end up with a liquid. And so the bottom line here is that as the bond energy of a material increases, okay, that means that the atoms are held tighter together, they're bound together. The melting point of the material will also increase. And when we're talking about high bond energies, we're talking about deep wells, okay? We're taking the absolute value here of, I'll just put here as kind of a reminder, we're taking the absolute value here of this well. So a sample that maybe looks like this, if this is A and this is sample B, right? The melting point of sample B would be greater than the melting point of sample A, because the bond energy of sample B is greater than the bond energy of sample A. It has a much deeper well.